Imagine standing on this vast, seemingly endless prairie, green and rolling, and then boom, the earth just drops away into a landscape so completely different. It's a place Theodore Roosevelt himself called fantastically broken in form and so bizarre in color. We're talking, of course, about the Badlands of western North Dakota, specifically inside Theodore Roosevelt National Park. So for our deep dive today, the big question is, how did these really unique formations, these like dramatic buttes and painted canyons, how did it actually happen? We're going to unpack the geological story, drawing from the sources you sent us, including some great stuff from the National Park Service. Our mission is basically to take you on a journey way back millions of years, exploring the powerful processes that sculpted this amazing terrain. Okay, let's unpack this.
Right. To really get how the Badlands formed and why they look the way they do, our story has to start a long way back, over 65 million years ago, actually. Paleocene epoch. This was, a totally different world. Right after the dinosaurs vanished. And the first big geological process we need to talk about is deposition. See, back then, the western half of North America was doing some serious mountain building, buckling up to form the Rockies. As those mountains rose, they were constantly being broken down. Water, wind, freezing, creating huge amounts of sediment, sand, silt, mud, all that stuff.
Okay, so mountains forming way out west are shedding material.
Exactly. And ancient rivers flowing east from these new Rockies carried tons of this material eastward, and they dropped it, deposited it in layers right here in what's now North Dakota. But that wasn't all. At the same time, you had volcanoes going off across the west, South Dakota, Montana, Idaho. Yeah, huge eruptions, spewing out massive amounts of volcanic ash. And that ash got carried here, too, either blown by wind or washed in by rivers, and it settled in like ancient lakes and swamps. Over millions of years, all this stuff got buried and compressed. The sand, silt, and mud became sandstone, siltstone, and mudstone layers. And those ash layers, they turned into this really distinct soft rock called bentonite clay.
Bentonite clay. That sounds important.
Oh, it's very important for later in the story.
Yeah.
But yeah, this whole process, this deposition, it just kept going for millions of years. Eocene, Oligocene, Miocene epochs.
Building up layer after layer, like you said. A giant geological layer cake.
Precisely. And what's fascinating is how each layer tells a different story. It's like reading chapters in Earth's history right beneath your feet.
So North Dakota wasn't always prairie then. What do these layers tell us?
Not at all. For instance, the sources mentioned the Pierre Shale way down at the bottom. That's from like 75 to 69 million years ago. It was laid down by a shallow sea, the Western Interior Seaway.
A sea in North Dakota.
Yep. Then above that, you get the yellow mounds. Those are basically old, weathered soils from that Pierre Shale time, ancient land surfaces. Then move up to the Chadron Formation, maybe 37 to 34 million years ago. That layer points to a hot, wet floodplain. Think swamps, ancient alligators.
Whoa!
And even these huge rhino-like animals called brontothers.
Seriously?
Invasive things. Then above that, the Brule Formation, maybe 34 to 30 million years ago. That signals a change.
Yeah.
It got cooler, drier, more like an open savanna, home to different kinds of grazers like oreodonts.
Oreodonts, never heard of them.
Unique creatures, sort of pig-like but different. And then the youngest layer mentioned is the Sharps Formation, 30 to 28 million years old. It even includes a layer of pure volcanic ash, the Rocky Fort ash.
So you really are reading a history book in the rock layers. Ancient seas, swamps, savannas.
It's incredible.
It really is. Each layer a snapshot of a different time, a different climate, different life. Okay, so that's the building up part, the deposition.
All right.
But that doesn't explain the dramatic canyons and buttes we see today. That layer cake needed slicing up, right?
Exactly. That's the second half of the story, erosion. And that really started to take over around the Pliocene epoch, maybe 2 million years ago.
Okay.
Initially, rivers were just kind of meandering across, slowly stripping away some layers, broad, shallow valleys. But the really crucial part, the thing that carved the dramatic shapes, that happened during the Pleistocene epoch.
The ice ages.
The ice ages, exactly. This is where it gets interesting. Huge continental ice sheets came down from Canada, massive glaciers. And they acted like giant dams, blocking the rivers that used to flow north. Like the ancestor of the Little Missouri River, it used to flow all the way up to Hudson Bay.
No way. The ice blocked it.
Completely blocked it, forced it and other rivers to find new paths, eastward, southward, eventually ending up flowing into the Mississippi system.
Ah, so that changed everything for the river's course.
Fundamentally. When the Ikes eventually melted and retreated, the Little Missouri was now on a much steeper path down to its new outlet, so it flowed faster, much faster. And with that speed, it started cutting down really deeply, into those soft sedimentary rocks we talked about earlier.
Especially that bentonite clay.
Especially the Badlands clay. When that stuff gets wet, it's incredibly slippery, very easily eroded. So the river and all its little tributary streams just sliced right through it. That's what carved out this fantastically broken topography that Roosevelt described, the deep gullies, the steep slopes.
So it wasn't slow and steady erosion, it was more like a powerful, rapid carving process triggered by the ice age changes.
Very rapid, geologically speaking. And here's the really wild part. The erosion rate in the Badlands today is estimated at about 1 inch per year.
1 inch per year. That sounds incredibly fast for rock.
It is. Compare that to something hard, like the granite in the Black Hills.
Yeah.
That erodes maybe 1 inch every 10,000 years.
Wow. So the Badlands are changing, like right now, as we speak, almost.
Absolutely. It's a very dynamic landscape.
Yeah.
What you see today is genuinely a snapshot in time. It makes you realize these places aren't permanent fixtures. They're evolving.
That perspective really changes things. 1 inch a year. It makes you wonder, okay, if it's eroding that fast, how come we still have these distinct shapes, these pillars and flat-topped buttes? It can't be just random washing away, can it?
Good point. No, it's not random. That rapid erosion makes the differences in rock hardness really stand out. This is where caprocks come in. You often have harder layers, usually sandstone, sitting on top of the softer clays and mudstones.
Like a little protective hat.
Exactly like a hat or an umbrella. That harder caprock shields the softer stuff underneath from the rain and erosion. So the surrounding softer rock washes away much faster, leaving these isolated pillars, spires, and of course the classic flat-topped buttes. That difference in erosion rates sculpts the shapes.
Okay, that makes sense. And the sources mentioned a couple of really interesting things found within these layers that also play a big role. Lignite coal and clinker, or scoria.
Yes, those are absolutely key to the character of the Badlands. Let's talk about lignite first. Remember those ancient swampy forests we mentioned from the deposition phase? Over 65 million years ago, think sequoia, bald cypress, magnolia trees.
Right, the hot, wet period.
Well, when leaves, branches, whole trees fell into the stagnant water of those swamps, they didn't fully decay. They formed thick layers of peat. Over millions of years, buried under more sediment, the pressure squeezed the water out and compressed this peat, chemically changing it into lignite. It's a type of coal, but it's pretty soft, kind of woody looking.
And people actually used it.
Oh yeah. The sources say Theodore Roosevelt and his ranch hands literally dug it out of the hillsides here in the 1880s to burn in their stoves. Free fuel just lying around.
That's pretty cool. Free heating, courtesy of 65-million-year-old swamps.
Kind of amazing, isn't it? And related to those ancient forests is the petrified wood you can also find here.
Yeah. How does that form?
Sometimes those ancient trees got buried really quickly, maybe by a flood or a volcanic ash fall. This protected them from rotting. Then groundwater, carrying silica, dissolved from all that volcanic ash, seeped into the buried wood. Over time, molecule by molecule, the silica replaced the original wood structure, turning it into quartz.
So it's basically a rock fossil of a tree.
Exactly. And sometimes the preservation is so good you can still see the growth rings, a perfect stone copy of the original wood.
Incredible. Okay, so lignite and petrified wood. But what about the clinker, the scoria? That seems really important for the look, the color of the Badlands.
It absolutely is. Clinker, or scoria as it's sometimes called, is responsible for a lot of the vibrant reds and oranges you see, and it forms through fire.
Fire underground.
Yes. Those lignite coal seams we talked about, the ones buried in the hills, they can actually catch fire. Maybe from lightning hitting an exposed seam or a prairie fire spreading down into it. And these underground coal fires can smolder for years, decades even.
Wow, burning underground for decades.
Yeah. And the intense heat from that burning coal literally bakes the rock layers sitting directly above it, like firing pottery in a kiln. This baking process turns the overlying sandstone and shale into this hard, reddish, brick-like material that's clinker. The colors red, orange, black, purple, yellow come from iron minerals in the rock getting oxidized by the heat.
So that's where those bright red tops on the bits come from.
That's often it. And here's the crucial part for shaping the landscape. This clinker is much harder and more resistant to erosion than the unbaked rock around it.
So it acts like an even tougher caprock.
Exactly. Sometimes it is the caprock, or it reinforces an existing sandstone caprock. As erosion wears away the softer surrounding material, these hard-baked clinker layers remain, forming the tops of many buttes and giving them their distinctive flat tops and reddish color.
So the buttes themselves, those iconic flat-topped hills, owe their existence and shape partly to ancient swamps forming coal, and then that coal catching fire and baking the rock above it.
In many cases, yes. It's a fascinating chain of events. Deposition, burial, fire, then erosion, revealing the results.
And there's that interesting detail about the north and south sides of buttes looking different, too. How does that work?
Yeah, that's another neat microclimate effect.
Yeah.
If you look closely at a butte, the north-facing slope usually gets less direct sunlight.
Okay.
So it stays cooler, holds more moisture, enough moisture often for trees like juniper or even ponderosa pine to grow. Their roots help hold the soil together, slowing down erosion on that side.
Right. More vegetation, less erosion.
But the south-facing slope gets baked by the sun. It's much hotter, drier, rockier. Very little vegetation can survive. So erosion is more active on the south side.
Giving it that stark two-sided appearance. You can really see all this geology playing out in places like Painted Canyon, can't you? The colors there are just stunning.
Painted Canyon is a fantastic example. You see the layers, the different colors from the minerals, the reds from the clinker. It's all laid out for you. And remember, these processes haven't stopped. The Badlands are still being actively shaped. You get about 15 inches of rain a year, but often in really heavy downpours.
Flash floods, basically.
Pretty much.
Yeah.
That water rushes down slopes, carving new gullies, and when water soaks into those bentonite clay layers, yeah, they get heavy and slippery, and you can get landslides, whole chunks of hillside slumping down. It's constant change. Construction and deconstruction happening all the time.
So let's pull this all together. The incredible landscape of Theodore Roosevelt National Park, these Badlands, it's basically down to two main acts in a very long play. First, millions of years of deposition, building up layers of sediment from mountains, seas, swamps, volcanic ash, trapping fossils along the way like clues.
Clams, snails, crocodiles, alligators, turtles, those champsosaurs.
Uh-huh.
Yeah, evidence of past worlds.
And then Act 2, intense erosion, kicked into high gear by the ice age's change in river courses, carving down through the soft layers but leaving the harder bits like sandstone and that fire-baked clinker as caps.
That's the essence of it. A long history of building up, followed by a dramatic period of tearing down, which is still happening today.
So when you stand there looking at the Badlands, what's the big takeaway? What does this geological story mean for you, the observer?
Well, I think it really drives home how dynamic the Earth is. Landscapes aren't static. They're the result of these immense ongoing processes over deep time. And it raises a pretty profound question, doesn't it? If these badlands are eroding so fast, remember that inch per year?
Yeah.
Scientists estimate the whole formation might be gone in maybe 500,000 years, which sounds like a long time, but geologically it's not.
Gone completely.
Eventually, yeah. Which means what we see today is pretty special. It kind of encourages you to appreciate this particular moment in its long history, right?
Wow, that puts a whole new perspective on it. Not just appreciating its beauty, but appreciating its temporary nature in the grand scheme of things. So the Badlands aren't just a place frozen in time. They really are a living, breathing well, eroding testament to deep time and these incredibly powerful natural forces sculpted right before our eyes, geologically speaking. It really makes you think about how even slow, subtle processes, given enough millennia, can create something so dramatic, so breathtaking. Maybe it inspires you to, visit the park and see the story unfolding. Because the Badlands aren't just a destination, they're like a living textbook, constantly being rewritten by the very forces that made them. Makes you wonder, what other landscapes around you are telling their own hidden stories?